Yeah. Hi, good evening, everyone. Welcome to the webinar number 28. APSDC is organizing series of webinars, panel discussions, interviews with industry experts, entrepreneurs, youth icons, by spreading the skills related to those skills. As a part, uh, the APSDC conduct one webinar on Earth observation through clouds. Today, resource person Mr. Rakesh Ban, head microwave systems and associate project or associate project director. India Space Research Organization. Coming to the track record, leading multidisciplinary teams of engineers to complete very complex synthetic apprentice radar of airborne and spaceborne satellite systems, in time and cost. And coming to the technical and managing roles, lead payload instrument of NASA synthetic aperture radar. Lead lead SAR payload dual frequency SAR, receiving Young Scientist Award and Project Group Award at ISRO also. So thank you, sir, for conducting this wonderful session for the AP candidates. This is very useful for ministers for enhancing their skills on observations through clouds. Thank you, sir. So now handovering session to Rakesh Garu. Thank you, sir.
Yeah, thank you. Do you need me to turn on the camera or it's okay with me? Am I audible?
Sir, audible, sir.
Okay, thanks for the nice introduction. So what I'll do is I'll just start sharing my screen first. And is it visible? Make sure before I start.
Yes, sir. Yes, sir. Visible, sir.
Okay, good afternoon to everybody. Let us see that what do we see the Earth observation through clouds? What does it mean? And what we have the tools and the resources and to see through the clouds. Now, have you any time imagine that when you see an Earth from a certain distance above the surface of where we normally have a lot of our day-to-day lives, you see Earth's actually mostly covered with clouds. And we need to see through the clouds to the surface of the Earth for a lot of reasons that I'll be covering. And there are a lot of reasons that why we should see through the clouds. Now, the problem is, can we see through the clouds any point of time and in any other? So the motive is to make you introduce to certain subjects of the remote sensing that we use for in the satellites, the airborne systems to image Earth, and the benefits of that. So if you see, when you go 3 kilometers up, probably most of you must have traveled through here, and once you see all the airplanes go up beyond 10 kilometers, and all the clouds are from 3 kilometers to mostly 5 kilometers or 6 kilometers. And sometimes when there are dense clouds, it may go up to 8 kilometers or something. But normally, all the clouds are cloud cover is actually from 3 to 5 kilometers or something like that. Now you see, you can probably see that if you take out your camera, your phone, and you want to click a photo, you'll not probably see, the surface of the Earth. Now, in case of floods, in case of cyclone, in case of earthquakes, volcanoes, the best place to see that, how do you rescue, how do you keep the rescue operations on, or how do you save people, and how do you assess the damage for different reasons. These clouds are going to be actually a problem for all of us. And this has been for quite some time that people realize that we need to see through the clouds. Why do we see that the clouds is a problem? But for Earth, I can see that all this life on Earth is because of the water and the air. And we need to see the clouds are pretty dense. The clouds are very good. And clouds are necessary for sustaining of the life. But the problem is, once there is a natural disaster, you probably you'll see that the clouds are a hurdle for us. Now, if you go a little up, you'll see that every night or from place to place, the monsoons are always part of the life. And in fact, without monsoons also you see a lot of clouds. It may not be thick around that area. But you see, from place to place, these clouds are always roaming around, and they don't allow you to click picture. So nowadays, everybody uses Google Image, everybody uses navigation, and if you go to Google Earth, you find a lot of good images. You never find clouds on those images, and most of those images are actually optical. Now, the problem is the wavelength of the optical region where we normally see things. Our eyes actually they see a particular spectrum of the range of the frequency. That's called the optical range, and the light from the sun, although it carries a lot of frequencies, but the optical range frequencies actually get reflected from as per the properties of the target, and we see that reflected energy, and we make an image out of it, and our eyes can process that. And that's where the whole world is actually organized around that. Everything in optical region is visible to us. Unfortunately, the clouds are also in that band that it looks white to us. That actually, in fact, the white is actually it reflects all the energy in the optical band to us, so it looks white. Now, if you have gone to Google, go to Google Earth, you'll find very, very clean images. And if you see those images, on the left side, you see there's a Google image, and it's a cloud-free image. And on the right side is one of the satellite images. It's a real satellite image, which has probably this lot of clouds around it. There are two types of applications what we do with the satellites. One is that we want to see the clouds for weather prediction. Those are actually mostly towards the optical regions, and we also want to see through the clouds. And that's what's the motive of the talk today. That we want to see through the clouds to see what is happening on the surface of the Earth. So if you see these two images are in front of you, the left side image is very clear and clean, and the right side image is a very neat of the Earth. So how does the Google get it? As I told you, the Google gets most of the images are in optical vision. Now the problem is, how Google makes it is they collect huge number of images. They have a lot of satellite data. They collect their own satellites. They have a lot of collaborations, and they get a lot of data. And finally, they select the batch of the image, which is actually cloud-free, and they make it available to you. Because the application is not for the weather predictions, and the Google does not. Google sells that different people. So if you see, you can go to the next and see how many images are useful actually in the Google posts on the web. It's actually more than 90% of the images are actually useless for the Google. So that's a huge data, and they can make use of it. Now on the right side of this beautiful Earth, you'll find a lot of clouds, and you cannot find. I don't think you will find any good tracks of this, through the cloud that you will be able to make use of. So what is the answer to it? Now the problem is how do we get our own applications done when the clouds are around. Now, if you want to see the Earth, there's another problem. If you want to go to the optical region for imaging the Earth, other than clouds, there's also day and night. So all the time, if you see the Earth goes through, half of the Earth is under the dark because sun is on the other side, and the rest of is available to you, and there are clouds. So probably if you see the cloud cover is mostly around 50%. You can go to the web, these are all captured from the web. So the cloud cover is mostly most of the time it is 50%, and then you have 50% daytime and night time. So the probability that you will get a visible, a good image of the Earth any point in time is only 25%. That is very small percentage that you have a possibility of 75% of not getting a Google image. I mean the good image because of clouds and 75% is actually a big number when you are going to a disaster. So if you see that particular disasters we are trying to talk about that we need to see through the clouds. Now in Indian context, floods, in fact it is applicable to anywhere in the world. But there are we need to talk about when we are talking India, we need to talk about scenario about disaster. So we have floods, we have fine clouds, clouds in some parts of Norway, towards Bihar side, and we have seen floods in Mumbai, we have seen floods. So we need to measure that, we need to see that, and unfortunately when the floods are there, the floods are caused by the rain, and when the rains are there are clouds. So the clouds, which are actually
Sir, sorry for inconvenience, sir. Hello, sir. Sir, voice is not clear, sir, actually.
So what do you want me to do? I need. Should I put my cam? Is it clear now?
Yeah. 1 second, sir.
Is it clear now?
Yeah, sir. Is it clear?
Oh, my microphone was very close to my mouth. Okay, should I continue?
Continue, sir.
Okay. So the floods, which are caused by the rains, and the rains are around, and then even after the rains, the clouds are always around. So that's going to be a problem for the rescue. And if you see the cyclones are also thick clouds, and you can see the typical image of the cyclone. You can hardly see through the clouds to see what is happening on the ground and how do you plan a rescue operation. We have tsunamis. We have seen tsunamis in Indian down south in India and towards the eastern part of India. And out of those, tsunamis, if it is coming like cyclone and tsunami is coming, it's going to hit. Then you can make actually forecast about the same lives. Of course, you cannot make it for the earthquakes. We don't have devices or or instrumentation or the science to predict an earthquake. But the problem is after the earthquake is done, whether you can do a damage assessment, whether you can see how much damage is caused by the earthquake and how do we get out of that situation and rescue people. And what was the epicenter? Are we expecting the similar type of earthquake is going to come in the same region? So these things are to be answered based on the image, based on certain measurements. Then you have landslides, you have lake outbursts, you have forest fires, you have oil spills, you have drought. A lot of natural disasters are there. So we are trying to find out solutions for these natural disasters. In terms of getting it, through the image, what we can answer, at least not the full. Okay. So if you see a typical cyclone, this type of cyclone is, it's a satellite imaging optical. So this satellite is actually this satellite is actually an optical satellite which has captured an image of the cloud, out of the cloud, and of course you cannot have an aircraft-based image during the cyclone because there's a lot of disturbance up in the air. So this type of image was captured by one of the satellites, and you can see through that there's an eye of the cyclone, and but you cannot see around the cyclone when the clouds are not there. Towards the left side of the region, there must be some the fast winds going on, and you can see actually the land towards the left side of the image, and cyclones actually are a problem when they hit the coast. So hitting the coast, that's where actually there's a lot of damage. So this is a typical image. So let us see how do we see the cyclones. The latest one is Okama cyclone. You can see that how do we prevent the human lives to be lost actually, and how we see the assessment of the property damage. So these again one of the typical images of the cyclone, and you can see lot of clouds around. So let's see the other things what we are expecting that the things will happen in terms of natural disasters like earthquake. This was this image of optical satellite looking at Indonesian earthquake which happened recently. So this is a typical image. You can see on the right side how much the damage has happened to the city, and on the lower part is the close-up image. If you go there with a camera on the ground and try to click the photo, you will not get actually a complete picture of the damage, and you will not be able to, assess the damage and the rest of it. So this is what actually we are trying to find out, the answer for. Now, if you see another image of the flood, you see the flood is flood is something which looks from an aerial perspective to the flood, which has caused a lot of damage around, and you don't know that people may be trapped somewhere. Okay. So let us see that if you want to image the cloud through the cloud, then it's almost impossible. And most of the time it's impossible only. There's no way that you can get out of it. Now there are other questions to answer. There are other questions like suppose you make a measurement of these things through the cloud. Then can you answer some other questions like suppose we have the sea level, which is actually rising, and with the current rate, it's going to be everybody is actually warning us. The sea levels are rising because of the ice cap melting and all the things. Although we have efforts, humans are doing efforts in different ways to avoid the situation or to come out of the situation. But the problem is not that we are coming out of the situation. Our problem for the scientists and the engineers is make an assessment, make a measurement at what level, whether it's an alarming level or is it okay level or is it something like we can live in the station for some time. So that sort of thing is something like what we can measure. And another thing is that water availability. When the situation changes around us, what is going to be the water availability to us for the human life? Yeah, is there anybody trying to talk? Any question? Okay, is there a problem with my mic?
Yeah.
Is it clear?
Yeah. Sir, please speak loudly, sir.
Okay, is it clear now?
Yes. Yes, sir.
Okay, far better. Okay.
Hmm.
Okay, so we are trying to answer some more questions when we make a right measurement of through the clouds and on the surface of the earth, and then we can make some more measurements and make answers available to us. Let me go through a typical image of the volcano. So the volcano is a typical and you can see there is a image in Russia. I'm not sure whether this is a satellite image actually. So this volcano erupted in 1994. I'm not sure whether it's active right now, but you see the optical region. You can hardly see through the cloud, the thick smoke coming out of it, and like a cloud, the fumes, and you can hardly make out anything, around where it is spreading to us, and whether the lava is actually coming out, which side it is going, and all those things. So the volcano is always a prominent image, and you can go closer to it. So another thing is like earthquake. As I told you, the earthquake is something which causes a lot of damage, and unfortunately, we have not seen earthquakes in the regions where there is no human population. So we have seen it is happening now, and there are some tectonic plates. We have made measurements of tectonic plates, and some regions are very prone to the earthquake. Although we cannot predict it right now, but but the earthquakes we need to see where it has caused the maximum damage and where the people are going to make their homes fit proof and what's the cost of the property for that and there are a lot of questions to be answered. So this is a typical image of one earthquake where in the Nepal actually in 2015 where 9,000 people died and it injured more than 22,000 people. So, these are right side. This is a web captured image of one of the same earthquake where they have tried to try to find out the answer of where it started, the epicenter of this earthquake, and after that, towards its spread and its angle of attack when it erupted. So it was something like, it caused actually secondary damage also. You can see there was an avalanche because of this earthquake, and there was a landslide, landslide or something like that. So these are secondary things, secondary damage. So to see that, the spread of this, it cannot be something like an exploding bomb sort of thing. It will spread actually towards different parts of the things where you can see the fault lines are. So let us see how this earthquake and all the things, how do we find an answer. Now I've told you about about the clouds, about our disasters, and what we're looking for. Now let us find an answer to image Earth or look at Earth remotely. What's called the remote sensing. This is a subject which normally all the scientists and engineers work on. That there is a way that we can sense objects remotely in a band of the energy which is different than the optical band. So if you see, the remote sensing is the science of making interferences about material objects from the measurements made at a distance without coming into the physical contact with the objects under study. So I can say the remote sensing is also can be done in optical vision. This is what is happening. You have optical image, that is the energy is emitted from sun, and you capture that image, in the optical vision you capture that image, and then that's also remote sensing, but that's in optical vision. But now we are trying to move out of this band, and once we come out of this band, then you can see that whether we can penetrate through this cloud, right? So there is a typical example of how do we emit the energy, how does it get reflected, and how do we capture that energy in a sensor, what we call that, either it's a satellite or it is actually an airborne one or a spaceborne one. So in subsequent slides I'll tell you how do we make measurements and can we make image out of it. Okay, hello. Am I audible?
Yeah, audible, sir. Sir, mic దగ్గరగా పెట్టుకున్నట్టున్నారు. ఒకసారి కొంచెం దూరంగా
Yeah,
పెట్టుకోండి.
is it okay now? Is it okay?
Yeah, sir.
Is it better than the previous?
Yeah, clear, sir.
Okay. Just a moment. Let me see if I'm using the right way of mic or it is something different. Just a moment.
Yeah, is my mic okay now? Is my mic okay?
Yeah, okay, sir.
Okay, they're better than the previous one. Okay, so let us go ahead with Actually, I'm sorry, my mic was, the webcam mic, so I changed it to the mouth mic. So yesterday we had taken the notes about it, but I'm sorry I did not select it properly. Okay, so let us find the answer for whether we can do a remote sensing through, through and make an image through a signal which we can transmit rather than depending on the sun. So the sun emits in the optical band, and we don't want to go to the optical band because we have a problem of reflection from the clouds, and we have a problem from up above the sky that we cannot see through the clouds. Now let us see what remote sensing or the other than the optical band can do for us. So we are talking about typically for the radar. So have you seen the radar? Radar is actually uh, an instrument for ranging, which was widely used during World War II. On the right top side, you can see a typical radar image. It's a ground-based radar. It actually transmits an energy in a band of 300 megahertz to around 2 or 3 gigahertz, and the energy comes back reflected from the object. And if you can measure the time between the transmit signal and the receive signal, you can probably make a measurement of the time that you receive back. And then, because the energy travels with the speed of the light, c that's called as 3 into 10 to the power 8 meters per second, you can exactly make measurement how far the object is. That's how the radars were used in during the World War II. It was widely used, and after that the radars found their use everywhere. Now you can see the radars embedded in the nose of every aircraft, whether it's a military aircraft, whether it's a civilian aircraft. Everywhere you can find a radar. And there are different types of radars also. Now you can see weather prediction radars, or you can see the cloud measurement radars. But typically the radar is a ranging device, which you can see on the ATC radars. You can find out that introducing you to the radars. Actually, my motto is that you see through the radars are all around you. And now the radars are coming into the it's coming into your cars. You can see that the radar, you can see that autonomous driving vehicles, they are finding use of the radars for finding the near objects, then the very complex modes of the radars. And you can find radars that are being used everywhere. But of late, from World War II, after that, when it was over, then people started talking about the radars can penetrate. Can we make use of the radar for imaging? If that would be possible, people thought of that we can see through and make the assessment of the floods. We can make assessment of the cyclones, earthquakes, volcanoes, everything. So typically the frequencies which at that point of time people were not able to generate high frequencies more than 1 or 2 gigahertz. But that was around in few megahertz. Actually, people were able to generate the frequencies. Now people can generate 10, 15, 20 gigahertz easily. So typically the radar band, we say we're talking about the radar bands which are actually from 300 megahertz to around 2 or 3 gigahertz or something like that. So maybe less than 10 gigahertz. That is actually where the radar bands are right now being used, because there is something called ITU, the International Telecommunication Unit, which actually gives the spectrum. You have the mobile phone spectrum, you have the spectrum for different applications, you have communication, you have a lot of other things. So the radar bands are actually to around 1 gigahertz, maybe around 10 gigahertz, you can use it. And let us first find out whether the radar can be used for making an image. So typically, around you can say people came with a concept that if a radar signal can be transmitted from a device or an instrument, and you can capture it back, typically in a side-looking way, the image on the left side of down left, if you see, you can probably make the measurement in spread in range, and typically see that you can make an image pixel out of the each return. So those experiments were done in 1950s or 60s. I think people were successful, and after that they thought of radars can make images. So this is a typical example of the real aperture radar, what we called as it transmits signal and gets by the signal. And why typically on the one side of the track? You can see an aircraft going, and there is a signal transmission reception on the left side of the aircraft track, because there will be an ambiguity of, if it is actually on the both sides of the track, there will be an ambiguity of the signal arrival time. The left side signal and the right side signal may arrive at the same time, and you don't know which side of the signal, which side of the target it is reflected from. So that's why typically they thought of it should be a side loop. And you can probably make assessment of the gradient of the pixel in terms of its energy reflection, and you can think of its reflection properties in that microwave range. So you call it as a real aperture image. But if you see on the right side, this is typically the real aperture radar image. You can hardly make a difference of the pixels through the visual range, that there is a road, and it is typically some field, or it's an open or a city area. These images were just a preliminary image where people thought of. And to increase the resolution, you need to decrease the footprint of your energy, which goes and strikes to the target. You need to concentrate it like a torch. The smaller are the footprint of the light energy on the target, the smaller is the resolution, and the best is the resolution. So that way people thought of. But at the same point of time, the energy from the sun and the energy from micro energy from a man-made satellite, or a device or an instrument, there is a difference. The sun gives you different polarities of this signal. It transmits in all the polarities. But when you transmit, there is typically a polarization associated with it. You transmit horizontally or you transmit vertically. So it will be easy for engineering students here to understand what a horizontal and a vertical polarization, or you can say a polarization vector of an energy means, electromagnetic energy means. So you can typically transmit in one polarization and receive in same polarization or different polarization. So that's why you can see there is a hazy HH written on the right lower corner of both of these images. So it's an H transmit and H receive. We'll go into the further subject of understanding what the polarization helps, how the polarization helps, and what the polarization means actually. Now, before that, can we increase the resolution of this image? This is, I think, one of the very complex subject slide I have for today. This is called the synthetic aperture radar. The previous one was the real aperture radar. It was just transmitting energy and getting it back. So after that, if you can increase the resolution, people found a way. That there was in 1950 around that there was a concept, but people could not realize it. Actually, around 1980s only people could realize these concepts about the synthetic aperture radar. So what people thought of is that if you can add the energy in the along track, dimensions of your flight track, you can probably add that energy in phase, and take because typically how the flight track is, or the satellite track is. You go in a straight line, and the distance to the target and the phase change because of that is going to be known, and it typically is a geometry calculation now, that if I take a range to the target, and if I take the range to the target from the far and the near end of the flight track, there is a relationship, a geometric relationship, and it changes. If you continue taking measurements to the target, to transmitting the energy and getting back the energy, you probably know how the phase is changing. So if you can take advantage of that and adding that energy in phase by data processing, you will be able to increase the resolution. And the advantage of that, increasing that resolution, is huge. It goes thousands times of increasing the resolution sometimes. So you can say typically hundreds of times you can actually do, but you can typically go, you can theoretically go with a very high resolution. So we are talking about the resolution of few tens of kilometers to few or maybe 1 meter or 2 meter of resolution. So that is the huge advantage of. It's effectively that you have a large aperture of the antenna, kilometers and kilometers, typically about 6-7 kilometers of the big antenna, which you cannot physically make, and you can synthesize it to in the flight track, and then you get the best resolution in the azimuth direction. That's the along track direction. So that's why it's called synthetic aperture. So I am synthesizing aperture by adding the energy in phase through the along track. So I leave it to, I will not go to the definition of mathematical definition of how the energy gets added and how do we, I leave it to the students to go to the net, read through the books and see how it works. So, but believe me, this is as complex as making a satellite. So processing the data, it's very complex. But then the advantage is huge. So, but it involves the Fourier transforms. So again, students will be able to tell, because they have, all of you must have gone through the Fourier transform, Fourier series. So it involves the frequency to time conversion, time to frequency conversion, and that's why people were very, it was a laborious job. As long as the good computers were not around to, because if you go for a Fourier transformation, though it's a recursive calculation, and for a huge data of gigabytes and gigabytes of data, so it becomes a very huge calculation. So it takes hours and hours and maybe hundreds of hours sometimes to process one patch of the image. So people were actually stuck with this for quite a long time. So they made optical processors, they made hybrid processors to get this resolution from synthetic aperture radar. And after that, finally, there was a breakthrough with the Kulitukki algorithm of Fourier transform that's called FFT, fast Fourier transforms. So that was a game changer in the synthetic aperture radars. Now, I will not also go into that direction, that we can talk about it in a different way, that how the data gets processed, how the Kulitukki algorithm works, or how the Fourier transform is done in azimuth and range directions, and how to get this. So that's a complex subject that typically is taught to the students who are typically in this field, working in this field. But today I'm just trying to introduce you to this subject so that you it generates an interest to you pursue through this subject, and some of you may be working in future in this type of the field, and so that unless you know it, you will not get interest to work on this. Now, going from from the real aperture to the synthetic aperture, going towards the inner details of the synthetic aperture, if you see the synthetic aperture, as I told you, stands for the synthesizing the aperture in the azimuth domain. So there are different sensors. Now we don't have any dependence on the sunlight. We don't have because it's like a torch. Like you illuminate yourself and you get back this. So you can imagine dark. That means one of our biggest hurdle is over. That we don't that 50% of what I told you, that I showed you an image of 50% of Earth is always in dark. So we got it through. So we have an answer for this. Now again, there's another thing that microwaves penetrate through clouds. It also penetrates to a lot of other objects, like the trees. If the wavelength is large, it can also penetrate through some of the objects, like you can say the fiberglasses or something like that. Where it's like an X-ray, like once you go to the airports, you see your all your luggage are actually scanned. Those are X-rays. So why they are scanned through the X-rays is because X-rays can penetrate. So X-rays are also the microwaves. So it's not like we started with the concept that we want to penetrate through the clouds, but these things can penetrate through a lot of things. So probably we can make science out of it. So if it can penetrate through the soil, if it can penetrate through water, if it can penetrate through snow, that's a good advantage for us. We can make secondary science out of it. So that's what actually is microsensors do actually. So we started with one objective and we're getting a lot of benefits of choosing these microwaves. Now going forward, there are different concepts and further advanced concepts of how the microwaves radars or synthetic aperture radars can be useful, that whether we can do a deformation study. Deformation is like the ice sheet melting, or the movement of a glacier, or the volcanic eruption. Because of that, there is a deformation. Biggest is because of the the earthquakes. So if you can make the assessment of the deformation of the land, you can probably make a lot of good decisions in terms of the rescue, in terms of planning cities around it, in terms of predicting what is going to be in the future. Now, another thing is that we have, as I told you, we have a few hundred megahertz, like 300 megahertz to maybe a few tens of gigahertz. We can generate the frequency, and we can we can make the measurements. But what is the frequency has to do with the physical parameters of the objects and the subject. You can say the subject study. Like we want to make a measurement of the deformation. We want to see through the clouds. Is any frequency going to work for us? So this is a very big answer for, question for you right now, because most of you have not worked on it. But let me tell you that frequency has a lot of things to do with the science what you want to get out of it. Say suppose L band. First of all, let me introduce the bands. The L band is actually the low frequency around 1 to 2 gigahertz. The S band is around 2 to 4 gigahertz, and C band is around 4 to 6 gigahertz, and X band is beyond 6 gigahertz, so maybe around 7 to 10 gigahertz sort of thing. So I can see these are sequentially, in the bands here, L to S to C to X. So actually, the choice of the frequency which your instrument or the payload or the satellite will have depends on the science. So I will tell you further through the image, what this frequency means in terms of the measurements. Now, we are also talking about the high resolution. So what is the resolution that we wanted to have? There is always a penalty that you have a high resolution, you have a lot of competition time, you have different parameters of the satellite, you have a huge data. And if you go into the resolution of a few tens of meters, you can always make it faster. The problem is not only that we make measurements, we have to know what is the turnaround time. Suppose there's a disaster. If there's a disaster, you want to come back very fast and make measurements. And if there's a disaster, continuing disaster, you want to make measurements every now and then. And even if you make measurements, if you click an image or you make an image, out of your measurements, there's again a chance that you will find that your image, if you get in tens of hours, if somebody is stuck or he or she needs actually a quick rescue, you'll not be able to see that after 10 hours or 15 hours or 20 hours if you produce an image and then make an assessment that is going to be useless. So all of these things come into picture when you talk about the resolution, you talk about the frequency bands, you talk about the processing time, turnaround time, a lot of things. So those are the secondary things. So first of all, let us concentrate on how do we make an image out of the synthetic aperture and how does it look like? I showed you one image back here, which is a real aperture radar image, and you did not, probably none of you must have appreciated this image, because we are now in the domain where in the time era where we have 40 megapixel, 100 megapixel camera in our mobile phone. So this is not really a good image. So probably it takes a lot of time, and that too in black and white. So because we see only reflection in terms of reflection in terms of the reflectivity of the target, not in the spectral domain. So that's why you don't have color. Now, if you typically see what a synthetic aperture radar image looks like, this beautiful image is captured. I think it's an X band from a German SAR. If you see, this is typically a polarimetric image. I'll tell you what polarimetric is in the future slides. I mean, subsequent slides. So this is typically an image which is, this area. If you see, there's a road, and it's not a road. I think it's an airport. So you can see typically, the area which is surrounded by some fields, and you can see some of the areas which are urban areas sort of thing. You can see buildings, and you can see the trees. This is typically a 1 meter sub-meter resolution image, an X band. So you can appreciate the colors here. So these are all false colors. I will not say I will say false colors for you, but these colors have a meaning in terms of the reflecting property of the target. So as I told you, the microwaves hit the target and come back, and the reflection of those microwaves from a target typically depends on the property of the target. Suppose you have a metallic target, it completely reflects back. Suppose you have a target like water, it completely absorbs the microwave energy. It looks black. Or you have a target which is not aligned towards your incident energy, something like you are transmitting an energy and it reflects back towards the other direction. It doesn't come back to you. So that area also, depends on the orientation of the target also. And now when we talk about the polarimetric measurement sort of thing, I'll tell you that the colors have a meaning in terms of its reflection property, that you can probably make a difference between a ripe crop and a growing crop and different types of crops. You can probably make measurements of The sweet water and salt water, you can make probably measurements of the trees and the canopy or a lot of other things. You can also make measurements of how dense the trees are, how dense are, and you can also, make a measurement of what is going to be your yield of the crop this year. Those are very, very secondary measurements that you can do. That's typically about science. So we are not talking about that today. And you can find a lot of answers. So now we can just quick wrap, go back and see where we started. We started that we wanted to see through the clouds. We want to get an answer for volcano. We want to get an answer for cyclone damage. We want to get an answer for earthquake damage. But if you see this beautiful image, you are probably finding different than much more than what you are looking for. So this beautiful image is an answer that this is the game changer in the field. That probably why should you use a camera now? Because this image is always available to you day and night. It does not depend on this energy of the sun. It does not depend on whether the clouds are there or not. So you can typically make good measurements out of it. So let me go further. That if you want to do this type of measurement, one image is not going to answer for you. So you probably try to see that you are going to make this measurement from a satellite. Now, if you want to have a satellite measurement, you have to probably launch a satellite. So you can have one satellite, or you can have typically multiple satellites. I'll tell you I'll tell you what one satellite and the multiple satellites mean. So this graphics is actually from the NASA website. It's in the public. All the things in my presentation today is actually from the public domain. This image is something like Earth is rotating, and the satellite is also rotating. And I'm not going into the subject that why the satellite is rotating in polar orbit, why it is not in equatorial orbit. So we'll not talk about that. I think you can find out the answer yourself, or else we can talk sometime else about it. So what is happening right now is the satellite for a particular target. Suppose over India, you want to capture an image. The satellite is not always over India. It goes over India for a couple of orbits, and then it goes from other parts of the world. And if you have a satellite for measurement around India, you should probably know how far you can make the measurement. Suppose you make an image, you took an image or took the data today. You can typically imagine that the satellite is going to come back maybe few tens of hours again over India. So you probably lost the time. And what we were talking about a couple of slides back, that you need a solution very fast, turnaround time in terms of when you are making about the disaster. If you are if you want to make a measurement about crop assessment, the forecasting of the crop production, a lot of other things, that probably you can wait for 20 hours, 50 hours. But if you are going to attend a disaster, you want to make an assessment, you probably will not like to wait. So the answer to this is that one satellite is not going to give you actually the solution to that. So you probably go for the multiple satellites. So if you have multiple satellites in different orbits, you can only see that the revisit time of the satellite or a particular region of your interest is going to be faster. So I will tell you in one of my last slides, I'll tell you what is the scenario today, what people are, trying to, how many satellites people are trying to put in orbit. You'll be surprised to see that there are thousands and thousands of satellites being planned in future. So this is what actually we want to go for, multiple satellite solutions. And now let us talk about coming back to the subject that SAR image looking through the cloud. This is a typical image taken from the web. Looking at, if you want to have an image from the space now, because we are not talking about the image through. You can always put a smaller payload on an aircraft and go over the region and image. That's a cheaper solution because aircraft is always handy, and as per the demand, you can go over and take the image. But the problem is in terms of when you're hitting the cyclone or you're hitting the disaster, you don't find aircrafts favorable situation for the aircraft to go over it. And another thing is that you want a huge area to be covered, so you need to go up in the air. In the space. So if you want to make a measurement through the satellite, you probably have to see that how much of swath I'm getting. How swath is actually the size of the image. So when through this along track, you can always keep on imaging. But across the track, what is the width of it? So you probably, when you're talking about the disaster like cyclone, you're talking about the disaster like flood, you're talking about volcano or I mean the cyclones, or you can talk about the earthquakes. So the size of the image is typically for cyclones and the floods are something that you need a huge swath. You need maybe hundreds of kilometers of swath sometimes, maybe tens of hundreds of kilometers sometimes. So at the same time, if you are talking about a volcano, it's a very small site, so you can probably work with around 10-15 kilometers of image size. So the swath is very important. So if you want to go for a bigger swath, one is that you have a revisit and you have multiple satellites, or you have one satellite with a larger swath. So typically, you can actually make a complex satellite mode where it can go across. You can step through the swath, get a lot of image across the swath, and you can probably reduce the resolution sort of things that not going today, that how do we compute the resolution when we are switching from one swath to another swath. That is again a complex subject, the higher subject for synthetic aperture radar. So typically we have zeroed down on that we want to go with the satellite, we want to go to a bigger swath, and as per the application we should be able to choose the swath. We also talked about that we need a multiple satellite solution. We also talked about that the aircrafts cannot go over the cyclones, and we also talked about the secondary applications of this type of data. So now let us come back to the mainstream, that how does it look like? This is typically of one of the Indian satellites. If you see this image is, I think it's a Mumbai area image. So there is an optical image, and this is again taken from one of the web but this is an Indian satellite. Both of them are Indian satellites. The background of this satellite, background image is actually an optical image. So you can see this is not actually typically an optical. This is actually a little off optical, but you can see the clouds. And over and above, there was an image captured by a radar. This is an Indian satellite, the radar image. So you can see typically when we scientists, application engineers did ortho ground rectification, and then they projected this image on the ground. You can see typically this black and white area of this Bombay, where there are no clouds. You can see clearly. You can make out this bridge. There's a sea link bridge, and these are the ships around. And you can see this is. I'm not going to zoom in here, but this is typically an image which is available. And if this image would have been taken the night, the background would have been completely dark, and still you would have seen this image. So you can see the power of this, the microwave imaging. Now, coming down to the subject of micro imaging, that now we have found a solution that we are able to see. We're able to see through the clouds with a high resolution. And now we talk about, the high resolution image, what we can make out of it. As I told you, there is a secondary science which can get out of it. Now, typically on the top side, if you see, there is nowadays actually we don't find in India the news about the oil slick, but in US and towards the Gulf region of or the Australian region, you will find there is an oil slick problem. This is actually an environmental hazard. Oil slicks can happen because of the man-made problems and because of the natural problems. You typically see that there are some people who are very active looking at. There are a lot of ships which are abandoned in the sea or near the coast, and there are a lot of ships with the crude oil, which get stuck or meet an accident or something like that, and the oil slicks into this sea. And there is a lot of marine hazard. A lot of NGOs, a lot of people work for this, saving the marine life. Down there, there's one more image. This is typically an Indian satellite image. You can see there's a volcano erupted. It's an active volcano, but you can see that previously I showed you one volcano image where there was a lot of cloud and fume coming out of the volcano, and you could hardly make anything out of that. Now you can see there is one. This is one of my favorite image. That there is a fresh lava coming out of this, on the right side of this image, you can see the fresh lava coming out. This is because of the polarimetric measurements. I'm going to talk about this in subsequent slides, what a polarimetric measurement is. But this is typically a radar image, which tells you that there is a lava, there's a fresh lava, and it is going towards the right. Now you know that where do you want people to be evacuated, where do you want to plan your rescue operations, because the volcano is going towards the right. Now, this is actually, these decisions are made typically on tens of hundreds of kilometers of size. It's not like typically for one field or something like that. These are big disasters, and this decision is also made on the big image. Now, on the right side, let us see what are the secondary science things, what we get out of these type of images. You can probably make a land deformation, as I told you. If you can measure uh, you know, um, the land, deformation in centimeters or millimeters, and you can probably make an assessment that the land is, because the land is making any change, and you need to probably make a decision about city planning. You must probably make decisions about people evacuation or something like that, or you can probably extrapolate that information to see what's in the future. Make measurements of the ice sheets, melting ice sheets, are changing, are the glaciers moving. That's called cryosphere studies. You can make measurements of the oceanography, like retrieval of the ocean physical parameters, surface winds, and wave spectra. You can make bathymetry measurements. You can make the ship detections, as I showed you in the previous slide. There's a ship. As you know, you can always find out what are the ships. In the dark, you will not be able to see them. So there are a lot of other signs like coastal process, how it is changing, the disaster response. I told you the ecosystem structures, and the last but not the least, the defense applications. So when we talk about the defense applications, defense also wants to make measurements. They want to see what is whether the enemy deployment is there, or the structures are there, or the equipment is there. So if you want to make measurements, the space is for everybody. You go to the space with a satellite and take image. Nobody will be able to tell you, or confront you that why did you take image from the satellite. Right now, the space law actually, it gives you it gives you freedom to click an image from the satellite, but you cannot physically go there with a camera and click an image. So defense applications typically depend on the satellite type of image, but they also have a problem like if the enemy is moving in the dark, or the enemy is moving in the dense forest. So they need this radar type of applications where the signal can penetrate and detect that. So I'll tell you that in subsequent slides that how do we meet those applications. Now, talking about the SAR image. Now, there are, before we go to typical SAR image, I'll also draw your attention towards that, the higher concepts of the SAR, synthetic aperture radar. So this is typically an image of the TerraSAR. This is a DLR, German Space Agency's image. This is one of their publicity image, you can say. So what they do is, if you can measure, the change in one of the image to the other image, or you can make out the change because of the movement of the surface of the Earth. You can make change because of the movement of the glaciers or something like that. That's called interferometry. So if you typically, how it is done is that suppose you take a photograph with your camera today, and after a few days or after a few hours, you take another image of the same area, and you overlay those images and see the change. Now, if you see that one vehicle has moved out of one of the pixels and has gone to another pixel, then you can make a change that one vehicle has moved, or one tree has fallen, or something is missing, or something has added into that image. Typically, the interferometry also works that way. You see a change from one image to the other image. But typically, you should see that the change has a lot of guiding parameters to see that how the satellite should take this image, how the radars should work on that. The change detection can happen in optical band also. But typically, we're talking about the radar. That one, you can see the track is taking one image through the clouds. It's a clear image. And another satellite is also tracking that image and taking one more image. And you can see there is an interferometric fringe. It's a phase change because of the change from one image to another image. So I'll tell you why this is done. If you can, if suppose the movement of the cryosphere, there's a movement of the glacier, there's a movement of the ice sheet, or there is a movement of the Earth's surface because of the deformation caused by the earthquakes. So you can probably make assessment, not probably, but I think nowadays it's an established science that you can make measurements, a correct measurement of how much is the deformation, and that measurement is typically done in millimeters, or few tens of millimeters to a few centimeters of accuracy. This is one of the published images of this, and they have been very successful in producing the interferometric map of the whole world. So you can probably go to net and search about TerraSAR, TerraSAR X, TerraSAR, Tandem X, and find these interesting images which are free. Now, going towards the further subject is that I told you the land information. So this is a typical image of the London image. This is one of the typical slides. This is again from the source. The source is actually from the net. You can go to the net and see. Now, if you see, typically this area, what you see at the red, is actually it's going to it's actually it's actually going down. Now you can see part of the city is actually in danger, and there are other pixels. These red pixels, there are around these pixels. People are not worried about. There may be a change in this building. There may be something like that. But typically, when you see an area, a whole area going down, and some of the like this, the blue coming up, so there is a land deformation. Why that is land deformation is there? There will be a lot of reasons, but there's land deformation happening. So you probably have to take a decision that whether we need to whether something big disaster is going to come, or the or volcano, or there is an eruption going to happen, or there is something in future, or it is going to stop, or it is going up and down. So you can see another image, which is actually again from Mexico City. There's a large change. You can see the measurement typically is from minus 2.5 centimeters to plus 2.5 centimeters per month. You can imagine that accuracy of the measurement through this radar image. Now you see that the one part of the Mexico City is actually going up, and other part is going down. Some parts of it are going down. Now, what is the reason for that? That's the secondary. That's beyond today's talk. But I'm just telling you, what actually the radar measurements are doing. Now let us recap once more before we move further. That what we started, where we started, we wanted to see through clouds. We wanted to find answers for damage assessment, flood mapping, deformation, and all other things. And we finally ended up finding out a lot of other things about the cities, the future disasters, and finding out whether we have enough food for the future, whether we need to go for, whether we need to plan the city in a particular direction, or we need to evacuate people. So these are typically that you get answers from these type of measurements. Now again, one more example, as I told you, the change deformation change measurement. There is a typical web image again taken from WebIS 2015 Nepal earthquake. You see this is an image overlaid on typically on an optical image, and I think these coordinates are put as per the physical location of this image. Now you can see these type of fringes. This is an interferometric image. You can see there are two images. It's a subtraction of the two images. One image was taken before the earthquake, and another image was taken after the earthquake. And you can see the phase change. You can typically talk about the two signals, the complex part r and theta, and another image with r and theta. You can see the theta difference. It's showing you some fringes here. And you can typically see that there is a change which is actually concentrated here. Now you can probably work out that with a layman's knowledge, you can say that this is the epicenter here. People may argue, the scientists may argue, no, the epicenter was somewhere else. That's the secondary matter. Now today we see that the epicenter looks to be here, and you can, through this fringe, you can also make secondary measurements that how much is the land deformation and what must be, whether there's any propagation of these fringes, like something like that. There is no propagation this side, but you can see the typical propagation this side. You can see that which side it was moving, and which side is more dangerous right now to for the people. So this was a typical image that I would try to draw your attention that the interferometry is something, and the land deformation is something which you should be very aware of, that this is a futurist subject and people are working on it. And I think this type of measurements are again right now opportunistic measurements, that people are not looking at every pixel of and every part of the land on Earth every point of the time. That is going to be the future. I'll tell you in my last slide that people are planning so many satellites in the future. So let us go back to what the polarization means. As I told you, the polarization is something which is typically associated with the microwaves. As long as your high frequency signal is inside the wire, it does not have a polarization. But when you start transmitting it through an antenna, it has a polarization. Polarization is whether it is an horizontal wave, because electromagnetic waves are transmitted through an antenna through a typical process. So that process is generates a typical direction of your electrical vector. So I will not go into the subject matter of, and that's actually a typically microwave subject. You can because being student of engineering, you may appreciate that the micros, when you go to the micros, you'll see that inside the waveguide, if you want to see that propagation of the waveguide, it actually becomes polarized signal, and then your propagation through the antenna, it becomes a polarized signal. So now when we talk about the polarization signal, so this is not the subject of today's talk, the polarization, but it is actually, I'm talking about it because it has a lot of things to do with the micro imaging. So typically, if you have a polarization, now you have a direction. You don't have, like sun is transmitting in all polarizations. You will not find a typical polarization. All polarizations it is transmitting and reflecting back, and our eyes also receive it through the through all the polarizations. Now you must have seen, when you go to the market and you buy a polarized glasses. That's very typical about the young generation today, and that's good actually. You have to wear polarized glasses to the light exposure of the light on your eyes. So you want to save your retinas. Now, what does it mean that when you talk about reducing the amount of the light which your eyes can see, you actually go with blurring of your glasses or a tinted glasses or something like that, which reduces the amount of the light. But that's not a solution, because at the same time you will start looking blurred. You will all the light becomes dim. But people have found a solution that if you can limit the light through the polarization, you will probably not see a degradation in the resolution. So that's why people wear polarized glasses. That's again a different subject. I was just trying to make you understand what polarization means. Now, talking about this polarization is like we typically talk about polarization in microwaves, horizontal and vertical. Horizontal is H and vertical is V. This is a typical definition of the engineers. How do we define the polarization? Now, the polarization can be, you can make a radar or an instrument with a single polarization that you transmit in H, you receive in H, like on the right side, or you can transmit in V and receive in V here. So you can make measurements. So, but how does it matter? So I'll tell you subsequently that how does it matter to the how does it interact with the property of the object. Now you can also make a measurement that you transmit in one polarization and you receive in another polarization that we call as HV or VH. So I'll tell you, this is called a cross polarization measurement. So I'll also tell you, how does it matter in terms of the image, and how does it make difference. Now let us talk about again the polarization. So this is a typical. We saw an image of volcano in optical band. So that's we crossed that subject now. We're not talking about that. We're talking about now two radar image or synthetic aperture radars image of a volcanic region. Now you see on the right side there is a single polarization measurement. Okay, so if you see there is a volcano, you of course right now this image is actually not. It's a 3 kilometers. I mean it's actually 1.5 kilometer image sort of thing. So you can typically talk about it is not how actually the resolution is much better than that. But the thing is you're not able to clearly see the image because this is not processed for the polarization for the resolution what a typically human's eyes actually are looking at. But this is for the science, so there's a different science out of it. So that's why each and every pixel is not very important right now here. So what I'm talking about is that this right side is a single polarization image. Whether it's an HH or VV doesn't matter. But right now, this is a black and white image, and you can see that you're not able to make out whether there's an old lava, the new lava coming out of this volcano is which direction it is. Now on the left side, there is again a full pole image. Full pole is actually HH, HV, VV, VH. When go back here, one slide back, this is actually transmit in H, receive in V and H both, and transmit in V and receive in V and H both. So in fact, we have 4 measurements now: transmit H, receive H, transmit H, receive V, transmit V, receive V, transmit V, receive H. So this is a full pole image. Now you can see clearly there's a difference. That's why I was telling you how the polarization interacts with the property of the targets is very important for the scientists. So now, if you see, typically now you yourself can make a difference of the different features in the image and make a science out of it that this volcano is active, which side it is active and which side is damaging, and what is its state right now. So this makes sense. So I think that's the biggest reason that we should go for a full pole image or a multi-pole image. I'll talk to you in the subsequent slides that we also want to make dual frequency measurements now. We also want to do actually a multi-frequency measurements now. But let us talk about right now the the different polarization image. So you are introduced to the polarization image now. So let us talk about one more comparison of the previous image to the new one. The left side is typically an optical image of the volcano. It's an active volcano right now, and you can see that you cannot make out anything. And this is actually an optical band. It probably has been taken in bright sunlight, and you can see the shadow of this smoke on this side. That means the sun is actually emitting from this side, and this is the best location that you can click a photo from this the other side of the sun, so that it is bright. But this is not of use to the scientists much because you cannot make out of anything out of it. Now on the right side, if you see, this image is a full polarimetric image of the same volcano, and you can see the peaks around it. There's no smoke, there's no fume, and you can also see the colorful image of the lava and the adjoining regions. You can probably make out that and make the measurements that are the science estimate, the classification of this image, that what is happening around it. It's a typical example of this. Now going further, you can with this land deformation, you can probably make an assessment of the water depletion. You see, this is typically about this is a NASA image. It's not a one image. You can see this is a series of images taken from 2000 to 2014. I think you can find on the net. You can find actually a video or the GIF on the net that how this deformation is changing in California. And nowadays the California is again in news because there's a lot of fire going on. And but the fact of the matter today is that the deformation is the California is going up and down. Probably you can see the millimeters, the 40 millimeters plus minus on the scale, but you cannot see on the minus scale, plus scale much. But it is actually between, you can typically say about minus 10 to minus 40 millimeters sort of thing, and you can see something red here. And 2002 to 2014, you see the change. It has completely gone from typically from almost down 40 millimeters. And I think why this is June only, because they want to compare in the same time period, because the seasons may also change this deformation. Typically, people say this is because of the water pumped out of from the ground, and the land goes down because of the land deformation happens because of the water being pumped out of this land, and at the same time there is a drought, and California has been under drought for so many years now, and it is drying up. So the common statement is like California is drying up, and you see because of that the land is deforming. Now California at the same time is actually a very earthquake prone region, and there are almost 200 small to big earthquakes in a day. So that's a different story. So you don't feel like, so that's why California is spread in it's not, there are no multi-storage building. But at the same time, you need to take into consideration, the steep lining has to take into consideration what is happening in California. So this is typically an image, and they were successful in taking these images every month, and from 2002 to 2014. And typically this is not from one satellite, this is from multiple satellites, of course. Now you probably saw through this that now you are in a condition to take a right decision. So let us go further, that whether you can make also measurements of by fusing the data. There are multiple techniques. And now if you see on the right side, there is an image, optical image, and on the left side there is a radar image overlaid or an optical image. So you can now make out the choice that you see this region on the top which looks black. These are typically the fields. And on the radar image, if you overlay that, you see you can make out the different fields have different crops probably, or different fields have different crops at different stage. or you can say there is a different. We're not talking about the property of the microwave signals in terms of its classification today, but you can make out that there's a difference. So whether this difference we can exploit to make science out of it. So why these differences are made, why these type of measurements are done is typically how useful it is. It's not like you say today that my field is not going to produce crop this year, or it's going to produce more crop this year. It's not typically about one person or a group of people. It's about the countries, the regions, complete, assessment of the food security or the damage assessment. Now, typically, you must have seen nowadays people are talking about the crop insurance, and the insurance companies have to make, or typically the government has to make this decision that what should be the right price for the insurance, what should be the bargain price for this, or people want to make a decision that whether there's going to be a shortage of the food this year after 3 months, whether we need to take a prior action for that. So that's called the forecasting, crop forecasting or something like that. And all these things actually are done by fusing the image, or typically on typical one radar image, or typically from multiple radar image. So I'm telling you, these are the big decisions taken on that. So let us do one more thing, one more round of. While we look at this beautiful picture, this is again, you can go to the net and see it. There was a huge satellite launched by ISRO in 2012. This is one of the best images taken of this satellite and published on the net. That there are few people. I'm not sure you find me here. I was probably at the location where the photograph was taken. So this was launched, and it was a huge success. And you can go to the net and see the importance of this satellite. That India became the fourth country in the world to have this type of technology. This is typically a radar, and I will show you one of the images of this radar. That was a very, very beautiful image, and this was way back in 2012, and it did its job for 4.5 years. Huge one. I'm talking about the huge one because subsequently I'm going to show you where the world is moving towards. So this huge satellite is it's actually hundreds of kgs of satellite, typically around 2,000 kgs or so. So so it costs very huge. It costs very huge. So why people are investing so much in this satellite? Probably you up till this point you'll be able to tell what is the importance of this cost. When we see that people are dying because of cyclone, people are dying because of the floods, and people are dying because of starvation. There's not enough food. The assessment of this food, land deformation, actually this cost is nothing in front of the human lives. So let us recap before we move further. Is that we try to find an answer that we want to image Earth's surface for typical regions of volcanic and a lot of natural disasters. We want to see through the clouds, and we ended up making measurements, secondary measurements of making measurements of the water, around us, the depletion of the water depletion, the cities going up and down, the deformation of the land, the cryosphere, the movement of the glaciers, and a lot of other things which can give us secondary answers. So let us go further. This is the product. Again, you can find it on the net, all these images. The recent one, we had typically something called not full polarimetry, we had a hybrid polarimetry. So again, I'm not talking about the hybrid polarimetry today because that's not the subject of the talk today. So if you see, these images are fused together, put together, all the images of the different areas. Now, this is not just an image like you see at camera image or optical image. These are false color images, and you can see, typically if you see the Antarctica, I'll show you further one more image of the Antarctica. You see the track. And if you see in the optical, I don't have an optical image right now, of the same region, but you will not be able to see this track. This is actually a track which probably the ship had gone through breaking the ice, and after that there was again the ice sheet over it. So typically the radar has captured the track beneath the ice sheet, saying that there is something not so thick around it. And this is actually typically all this is ice. This is not something rocky. This thing, Antarctica is all ice. So over the sea, you can make out, and there was a ship. Then probably you can make a measurement saying that there was something which happened, which we could not see through an optical image. And typically, if you talk about, I don't have an Amazon image here today, but Amazon, you can make out there's a new forest and the old forest. You can make a difference. that there was a deforestation and there was an afforestation again, and the new trees and the old trees you can typically make measurements on the huge landmass of hundreds of kilometers, or typically tens of thousands of kilometers sometimes, that there is a vegetation change, there is a new vegetation or the old vegetation. So you can make measurements of that. You can see these beautiful images. So there is typically an oil spill. If you go to the optical domain and see an image of the optical, you will see probably a sea. You will not see this. This was typically captured over Norway. There is an oil spill here, and you can see the oil spill has spread in one direction, maybe because of the wave structure, and you can probably see how much damage it has caused. And oil slick is actually a big application of the radar. And you cannot see it with even in the daylight. You cannot see it through with an optical camera. So now another thing is that you can see the Andaman Seas. You can see Andaman Sea again. This is a sea image. You can make out the differences. And there is if there is a shallow sea, you can make bathymetry measurements. You can see how the surface of the sea has changed, or the surface of the sea looks like. Now, going further to this, you can see, as I told you, the radar signals penetrate. Now, this is again one of the Indian satellites that we're talking about, and this is a famous stadium. Right? Have you seen that typically this stadium is having trusses? You don't see from an optical image, you will see a white, the roof of this stadium. There is typically a fiber glass or something like that on this roof, and you don't see what is inside. But because the radar signals have penetrated, you typically see those trusses. You see, actually, it is transparent to you. So that gives us a different scenario, that you can probably see through things where you need to. So right now, this image does not make sense that you are looking at the trusses, but because the radar signal penetrates, it becomes interesting to see where you want to see through the things, like the soil moisture, or you want to see something which is little embedded inside the soil, or I have an image somewhere of the desert typically by a foreign satellite, which actually penetrated the low frequency, penetrated beneath the sand, and it has a very nice view of how the surface looks like, below the sand. So I'll show you if I get time in subsequent slides, but that's actually in the backup slide. So going further, as I told you, I'm going to show you an Antarctica image again. This is again Indian satellite. You can see our Indian site is somewhere here. The Bharti base is here. You can typically see, there's a route here. As I told you, there is a sea route, and the ships can ship route and here. And another thing was. So another thing was that you can make measurements of the sea ice, glacier, ice deformation, icebergs, snow cover, ice sheets, etc. As I told you, but this is typically an Indian satellite, and you can see the other bases here. And of course, this is not a very high resolution image because this was taken on a huge region, but this is a radar image. Now you can probably you can add that radar images are also colorful in terms of polarization at the bands. Now let us go further. Measurement of delta. So you can see this is again this part of the India. This is a background image, is the Google image, and again this is done by the ISRO scientists. So I forgot to mention their contribution here, but this is again on the web. So this you can make an estimate that how the delta is changing. So this is again interferometric SAR, that there are typically more than one image. So you can see that you can typically study the delta, how the delta is changing, and how the marine life is changing around it, how the mangroves are changing, and why this is so important is not also the subject matter today, because deltas are very important in terms of the life around it, and how people are also arguing about how the delta is changing towards the Nepal, and how the delta is changing towards the India. And there's a lot of there's again a different subject that we should not go into today. But you can make right decisions, that people are talking about the mangroves are dying towards India and it is flourishing towards Bangladesh. So you can probably find the answers here. You can probably find take a right decision, that where we are wrong or where we are right. Okay, so this is again a typical image. So as I told you, the mangroves, you can also make the difference. This is again an ISO image, so it's again on the web. So this is a classification. So classification typically is about, you can say, the dense mangroves and the sparse mangroves. Can you see that the mangroves is there? Okay, we made a measurement. I told you in the previous image you can make a measurement of it. But can you talk about whether it is dying, whether it's a dense or it is sparse or what? So you can see typically again our Indian satellite image. So you can make a difference. This difference is something like you can talk about, there is a dense somewhere, there's a sparse somewhere, there is some sand beach or something like that. So you can typically talk about the marine life. You can typically talk about the mangroves and the importance of the mangroves. So typically this subject of mangroves, and this is the subject of the environmental scientists. But our job is to see that the environmental scientist is given the right data. So again, one more typically where India stands in terms of the damage assessment. So it's not like you made an image, you produce an image and gave it to the person. The person should be able to use it. The person is, who is the person? Who is the user? Users are mostly the government agencies. Users are somewhere some NGOs. You have to give them a solution. You have to give them actually a right solution on the table that they can take a decision. You cannot ask them to do a science over the image and make a decision after that. You have to make a science for them and make it available for them to take a decision. So typically you can see the ISRO image again from the web, published image. So you can see there are, as I told you, the previous slides, there is a fusion of the optical and the radar image. You can also see the undulation of the surface because of the floods. Also see which the breakage of the and barricades. And there are different satellites which go into that charter, and there is a disaster management program where India is a charter in the world also. We're typically talking about that there is a program in place, and what the scientists are actually investing their time and money. So let us go to one of the typical this is again one of the collaborations of ISRO's with NASA. Going to two types of collaborations. One is already executed, another is going to be executed. This is a NASA aircraft, so we wanted to make actually one radar on the NASA, mounted on the NASA aircraft. You can see the belly of this aircraft carries actually their pod and the antenna. And our team went to California and tried to execute it. And why this is important, I'll tell you. So this is again an ISRO image. One of our great scientists and engineers has made it. See, typically as I told you, we talked about polarization. We talked about V and H polarization. We talked about the full polarization. We talked about hybrid polarization. Of course, we did not went into the subject matter of how these polarizations are generated and how these polarizations make different signs. But we prima facie saw how these interact with the property and the property of the targets. You can see over and above that, if we can measure different frequencies, like I told you about C band, L band, S band, X band, and of course we did not talk about the properties of the signals band frequency interacting with the properties of this the target. We did not talk about it, but prima facie I told you, different frequencies have different characteristics of reflection and penetration. As you go into the lower in the frequency, is that it will penetrate the target, and as the frequency goes high, the probability is that, and the tendency is that it gets reflected. So typically when you are talking about the applications where you need to penetrate, like the soil moisture, like you want to penetrate somewhere through the ice or the glaciers, or you want to see penetrate through the water to see the ocean or something like that, you need to go to the low frequencies. And when you talk about the frequencies, you typically have the applications for the defense. You want to see only the surface. You don't want to penetrate. Now, talking about this, if we can, as I told you, different polarizations, merging them together, and you get a different size, you get different colors. At the same time, now the scientists are going towards the different frequencies also. Of course, there were efforts with Germans long back. There were efforts to have, and now also they are going for different bands. Like I have an L band image, and I have an band image, or I have a C band image, and I want to overlay those images and see what they change. typically this collaboration with NASA right now, which has been executed and it is going on, is on an airborne aircraft. We are having a two frequencies radar. So this is actually an S band, which is and another one is an L band. And this the difference is that what NASA is doing, what Germans are doing, what other agencies are doing for the different band image is like they generate one image and then they generate another image. The typical part of this collaboration is that these images are generated at the same point of time. The two frequencies are actually they are generated at the same point of time and they are captured at the same point of time. Now you can see typically that why this is done actually at the same point of time is that we don't want anything to change on ground. In fact, even in the single vehicle or something to move by the time we capture another image. So the best way is that you do it together. So typically this is one of the images. So you will see further more images in future on the net, and this is well published on the nets in the NASA website. You can see there are these structures. These are actually the fields and in the California, and you can see here the fields are not visible. And this is a different band, and this is a different band. This is S band, this is L band. Now you can typically make a different science out of it. So that people are looking at it. Of course, this is not an established science right now. So I am bringing you towards the higher subject now. We end this talk today. But I am bringing you to the subject where you see that the bands are now they represent a different story now. So typically, you should once you start your careers in this type of domain, so you typically will see not a single pole image. You'll see typically a dual multi-pole image and multi-band image. So most of you may have generated interest and opportunity to work on this type of data. This is very, very interesting data. Now, this is one of the, as a filler here, that went to Antarctica also to capture sea. And this is the location, the Fairbanks, where our team went. And this is one of my phone captured screenshot showing the live location inside the aircraft. We went deep into this Arctic region, and where there is mostly dark. The sunlight is far around 700 kilometers or more than that, a bit more than that, thousands of kilometers from the Fairbanks of the Alaska. So you can see a temperature range of that. We went into the winter season. It was minus 35 degrees C. So our team could survive, fortunately. One of the images which I took with my phone from, through the aircraft window. You can see how this was just at the sea ice just starting from this edge, because after that there was a dark. So you can see typically how the sea ice looks. And now if you go towards the measurement of the sea ice, now there are channels. You don't know whether there's a thick sea ice or something. This is a big science. Now if you see the further image, so this is one of the typical images. You can again go to sites and find out this type of image. I'm not sure. These images are now actually, this data is free to all of you. Maybe if you have generated any interest in getting this data, you can just log in to the NASA website, JPL archives, and get this data. So this is typically the difference of the two bands over the sea ice. So now you can make out, the colors you can make out. It's not only about colors. It's about its reflection properties in terms of the phase, or the complex phase is changing. And you can make out, there are a lot of scientific techniques to see how and what the parameter difference is between these two images. So I think the world is moving towards dual band or multi-band, and you can make a lot of science out of the multi-band, multi-polarization. So it's a manifold, n-dimensional data now. Now, why do you want to make this Alaska measurements? Why it is so important is that we have a sea ice. It's a frozen water, actually sea ice, and as the ice is less dense than water, it floats over the ocean. So it typically is actually that over the winter region that it freezes over the ocean, and you can make you can make the measurements. But the problem is the sea ice covers only 7% of the Earth's surface, and about 12% of the world's ocean. So if such a huge cover is actually such a huge area is covered with the sea ice, so it typically should make a measurement of the ice sheet and get an idea that how much is the sea ice is increasing Are the polar cap ice is increasing or decreasing? And it has a, you must be actually hearing the news. You must be hearing a lot of things about the environmental protection, about the you can say the global warming. So everything is actually decided by the Arctic and Antarctic. So this Arctic and Antarctic measurements are very important in terms of the ice measurements. That's called cryosphere science. So typically you will find some terminologies here which we are not actually in the engineering career. You may not have seen it or gone through it, but typically you'll see it when you generate interest and go through these type of subjects. Now let us move out from the microwave image. Let us move out of that. We did not talk about the cyclone. We did not talk about the cyclone. How do we make measurements? We talked about, let us recap once more before we go into one of the last subjects, that we started to look through the image, look through the clouds to see the Earth's surface. We started our subject with that. We wanted to make a good measurement. We wanted to find answers for a lot of natural disasters. We ended up making measurements through the image for a lot of other secondary science which it is giving. We wanted to we started to think about the secondary science in terms of making assessment of crop assessment, the land deformations, a lot of other things. But now the last thing which is not happening on land is actually the ocean. You can say the surface of the ocean. Cyclones. You can see all the cyclones are actually generated over the ocean surface. It's not on the land surface, and when the cyclone comes towards the sea, it hits the land, or it hits actually the coastal area. Then actually that's called a landfall or something. It's called landfall actually. So that's where it becomes dangerous for us. But can you track it? Can you measure it? And can you make a forecast? So that's what actually is a different subject. It's called microscatometry. You can typically take an optical image. You can take an optical image of the cyclone, and that has been successful. People are, as I showed you a couple of images before we started in the initial stage of this presentation, that we are going to make. We see the optical image. That's where actually world was looking at. It's a few tens of, one decade or 2 decades before. So now we are moving towards the microwave side, that whether we can make measurements of it. That's called microscatometry. Actually, as I told you, the microwaves penetrate the atmosphere. It penetrates the clouds. But if it penetrates the clouds, how do you make measurement of the cloud in the cyclone? Because you are typically measuring the cloud now. Now the issue is, when you take an optical image, you will see clouds, but you will not be able to make out the cloud is moving in which direction, how this cloud is moving, and towards. You have to probably take many more images in subsequent, the time series image to make out that where this cyclone is moving. But if you can make an image from a radar sort of thing, which shows you the direction of the wind, which shows you the direction of how it is moving, where the eye of this cyclone is, and then probably make a correct measurement of how this is going to be in the future, the movement of this cyclone, and where do you want to see the people should be evacuated. And typically you have seen people say a couple of days before the cyclone is going to hit, people make forecasting. They announce warnings that the cyclone is going to hit the coastal region, typically this coastal region or that coastal region, and people are typically evacuated from that region. And we have seen cyclones from every year. We have seen big and small cyclones, and we have also seen in 90s when we used to have cyclones, thousands of people used to die, typically in Odessa side. Now, if you see that was the story in 90s, but after that, we also have a couple of instruments, a couple of satellites, very good satellites in space, and we could establish the science, as the world is also giving us, other different agencies are also giving us data, and scientists are working on that. And if you can measure, you can make a measurement of this through scatterometer, you can make a measurement of the cyclone correctly. You can save a lot of lives. Nowadays, you will see that recently there was a big cyclone going to hit towards the eastern coast of India, and typically scientists could predict where it is going to hit, typically, and people were evacuated. And you have seen 4 or 5 people only, the casualties were there, and compared to 90s when we used to have 10,000 casualties or 5,000 casualties. So this is actually a huge change in terms of the measurement of the cyclone. So typically, I will not go into the subject of how the scatterometer is built. There are different concepts. You can go to the net, but typically, broadly, you can say there are two types of scatterometer. One is the fan beam and another is the pencil beam. But this is very complex subject for you today to go through this technical matter of how this pencil beam and fan beam looks like. But what our intention is that whether we can make measurements. As I told you, the microwaves penetrate the clouds. Now, how do we make measurements? So the key is that if you can measure the surface of the ocean, you can probably make out what the wind is going towards and how the wind is behaving. So the interaction of the wind with the ocean surface is a known phenomena. So when the wind moves, it creates ripples over the ocean surface, and those ripples are and the height of the ripples and you can say the wavelength of these ripples are directly proportional to the speed of the wind. Now, if you can measure the roughness of that surface and the direction of those waves, you will be able to make a correct measurement of the wind. So typically, if you can make that, and that is an established science now, that when the wind is moving over the ocean surface, you go with the satellite, a micro satellite, take the measurement of the surface of the ocean, and if you see the ripples of typical behavior, and you compare those responses with the model functions, and you can probably make a very good measurement. I'll show you an image of the Indian. This is again on the net. It's a time series image that how the scatterometer measures the wind surface. So everything is on the ocean surface. You can see nothing is on the land surface. So as I told you, we are making measurements, indirect measurement of the wind through the scatterometry by measuring the surface of roughness of the surface of the earth, surface of the ocean. Now you can talk about surface of the ocean is something like it's not now we cannot talk about this measurement or this the land. Now you can see there are typically these red ones. You can see this eye forming here, and these are some cyclones starting over the ocean surface and somewhere dying in the ocean surface itself. So the cyclones which are actually bigger than what of the particular size, like this red is making bigger shape, and it's building actually for days and days, and after that it if it moves towards the land surface and coastal area and starts hitting it, then there is a dangerous situation for us. But otherwise, people start tracking it. They don't give warnings. 3 or 4 days or 5 days before the cyclone starts hitting the coastal area, because people cannot make out that whether it's going to come to the coastal area or it's going to die in the ocean itself. So typically, this is actually a data which you can go through. This is actually published on net. You can talk about scatterometer visualization data, and this is a very nice image that made by the scatterometer, and it's an established right now. Our scatterometer is in the orbit, and I'm not sure you have this data free, but you can go to our sites. Typically, our Mosdec site, you can go and see the data. Now, going towards few last slides, I think 3 or 4 slides left, and we are also hitting towards the end of this session. Now, typically, I told you in the initial that you should have multiple satellites or single satellite, but that is also not going to solve your problem in terms of that you have multiple satellites. Suppose you have 2 satellites or 5 satellites, but typically somebody on the Earth is in the trouble because of the disaster, and you say that suppose any of our guys around is in trouble, and we want to take a measurement immediately with a satellite, and our satellites are busy somewhere else. They are not over that region. But at the same point of time, suppose there is a friendly country whose satellite is going to pass over. Can we ask them to take an image and give it to us in terms of disaster? So it is like joining hands for the sake of humanity. So there is a charter. There is a disaster management charter in the world, and India is also signatory to that. And our satellites, suppose the satellite is not typically only for the common purpose of that I told you, about cyclones and disaster and floods. Satellites are basically meant for some science, like the food and food security, like crop production, like soil moisture, a lot of other things. But if you have, and a satellite is not something like you ask today, right now, 1 hour before, and you say, okay, I want this image, and satellite goes and takes that image. The things are programmed, the things are planned months and weeks away before that. So So typically our satellites are anybody's satellite in the world is always programmed for 6 months, 1 year. So it's busy. Now, if you want, and the disaster does not wait. Disaster can hit any point of time, and if somebody is in trouble and they want to make help of the satellite which is passing through, there is something called emergency response. India is again the signatory to it. Suppose our satellite is busy taking science and it is busy with scientific people making some study. We have to interrupt that measurement and we have to give that services to the charter. And at the same point of time, if we are in trouble, we have to get the data from the different satellites. They are also signatory to that. So it is like joining hands. So we are not alone. The Earth belongs to everybody, and the disasters also does not see the boundaries. So this is just one slide. This is again a constellation of the satellites, the different satellites. So you can see Indian satellite typically was megatropics here. So we were giving it. I think reset somehow was also part of it. I'm not sure. So this is like, you can see a lot of other agencies here who are part of this charter. And this is not the latest one. Now, India had a big collaboration with France, making one satellite that I told you, the megatropics. So there was actually a 50th year space cooperation celebration between France and India. So both of the countries released one stamp. You can see right side there's an Indian stamp, on the left side is the French stamp. So it's a postal stamp. So this is actually a good gesture from the French side and the Indian side. This was typically, I'm not sure you find it on the net. Of course, I have taken it from the net, so you'll be able to find it. Now, what is in the future? So as I told you, the NASA in ISRO is also collaborating with NASA for an airborne, so which I showed you the data. But there is a bigger collaboration than this. There is something called NISAR. There's the NASA ISRO Synthetic Aperture Radar. It is again a dual band, multi-pole SAR, which is going to make a huge measurement of thousands and thousands of kilometers, and it is going to make complete measurement of the Earth in 12 days. So you must have heard the news that before we go to one of the new subjects, you must have heard the news that NASA is going to collect the data of this NISR equivalent to the combined missions of all the NASA satellites till now in 1 year. So you can imagine the amount of the data we are talking about. We are talking about terabits and terabits of data. And there is not even supercomputers enough with NASA right now, our Indian side, because we have a joint collaboration, that we can process a whole of the data by the time the new data comes. So there's always going to be a spillover. So there is, we are talking about the grid processing, we're talking about the community, joining together, offering their computers for data processing. So there's a huge data, and there's a huge network. And this data is also going to be free, and a lot of scientists, I don't know whether some people of my friends will be actually looking through YouTube right now or LinkedIn right now, that this data is going to be free. This data is going to be, for this, it's called the free data because it's going to be a community data. But different scientists will use this data for the different purposes. So this typically, I'll show you an image. Here it is an image. Before I go back one slide after that to introduce something different. So this is going to be launched in 2022, and as typically, this is the latest artistic image of this photo of this satellite. So it looks like, so we are just launching it, we're just getting it ready. So before before I show you my end slide, this is a NASA mission, SMAP, we call it as, it's actually an active passive. So as I told you, we were talking about the polarization. We were talking about different dual and single and full polarization. Then we talked about that multi-band, the different frequencies clubbed to in one satellite. Now here actually there is one more mission called, it's a radar plus a radiometer. It's a passive measurement and active measurement merged together for the soil moisture. So I will not also go into the science how it makes the measurement, but I would draw your attention that radar images are not alone nowadays. The radar images are merged with different data. It's merged with the passive imaging. It's merged with, fused with the optical data. It's fused with multi-bands. It's fused with multi-polarizations, and to get most of the science out of it. So now let us, this is my last slide. I think we are hitting 5:50, so I'll leave 5-10 minutes for this, for discussion. But let me explain here that we are talking about thousands of satellites in the future. typically about the radar missions. You can see this. There is an Amazon. There is a Kepler Space which is planning to have more than 30 satellites in next 3 to 4 years to go for an expand radar. We also have a Japanese agency, Synspective, is planning to have a constellation of SAR satellites. They're talking about the 25 satellites, but that's not all. You see, the Amazon has recently got an approval in the US that they are going to launch 3,236 satellites into the lower Earth orbit. Of course, these are not radars, but you see the number of the satellites we're talking about. OneWeb is planning to launch 46,000 internet satellites in the next 1 decade. And if you talk about SpaceX launching Starlink, which is like the internet IoT you're talking about, they are planning to launch 12,000 satellites, and they have already started launching 775 satellites already launched. And we are talking about they are also having a possible extension of 42,000 satellites. Now, if you see these type of satellites, the orbits are locked. There's a huge number of satellites coming into this orbit, and there's a huge market for it, and everything on your in your hands will be linked with the satellite. So and there are now companies coming up talking about the space junk. Now, this is a typical image I made, that you have to dispose of the satellites, and that's going to be the next future problem for us. So that's the end of my talk. I leave it to this audience if they have any questions. Okay, do we have the questions? I'm afraid I'm not able to hear you.
Yeah, audible, sir. Dear candidates, any questions, any queries, please raise hand. I will give the permissions. Directly talk to Mr. Rakesh, sir. Anyhow, your doubts, please raise hand. Top of the your right side is second options, the raise hand. But anyone put in the chat box. So Rakesh sir, actually
Can you help me repeat?
two persons put in the chat box, sir. What programming language does ISRO prefer of working on as well as for recruitment? One question.
Pardon, can you repeat the question?
Sir, you see also same, sir. Chat box. Close this PDF.
Okay, the chat box. Okay.
Yeah, chat box, sir. Chat box.
Okay.
Srinath Malina.
Okay. So, what
With
programming language does ISRO prefer for working on as well as for the recruitment? Okay. So, this is typical, not about the talk today. So, Srinath, we don't use a language which is typically talk of the day, like Python or something. Use typically C and the old language, and but there is no binding on using different language. People write MATLAB. People can also use the recent language like Python or something else. So there is not something like, we don't have standardized language of a programming language that we are using. But we have seen MATLAB and C is very standard language people use. And recruitment regarding that, it is actually through Times of India or all the leading newspapers of India. You can find the advertisement, and the process is that you have to apply against a recruitment ad, and there will be an exam, there will be an interview, and typically if you pass through that, you are done, right? Is there any other question? Okay. So, is there any question coming from the YouTube viewers or Facebook reviewers, right? Because I cannot see that, so you have to tell me, is there any question about that?
Sir, thank you, sir. Thank you for your wonderful session for today. These
Thank
two
you.
hours. Mm. Sir, some people are asking the PPT.
Yeah, so I don't think there is something which is very, very typical about PPT. It's all from the web because we do have restrictions of any PPT being circulated from the ISRO side. But I don't think that my PPT contain anything which is not on the web. But anyway, I can give you a simplified version of it. So you can
Yeah,
just
yeah.
keep it.
My mail ID is sir ashok.b@apssdc.in.
Yeah, why don't you give me a test mail and then I can reply it back, right?
Yeah, yeah. Okay, sir. Okay.
Okay,
Okay,
so
sir.
are we at the end of the session?
Yeah, yeah. End of. Okay, sir.
That's good. Thanks a lot. Thanks a
Okay.
lot.
Okay, okay. Thank you, sir. Thank you. Thank you very much. Dear candidates, please see that put in the chat box and feedback from dear candidates. Feedback from put in the chat box. Please fill the form. The certificate is not working. 1 minute. No working. Already some peoples are giving the feedback. Once again, refresh your page. After I will give the asking this sign in. No, it's working. Yeah, yeah. Your certificate is provided maybe next week. Next week, surely the certificate is provided. APSSDC is future also this type of workshops is conducting. You see that APSSDC.in portal, APSSDC.in. These websites like that more details info. You see that this APSSDC.in. Facebook also. Another one, anyone see that the APSDC programs is webinars YouTube. Please go YouTube and searching the AP State Skill Development Corporations. Is number of webinars videos that okay. But this info share to your friends also. Your friends or faculties also this type of webinars and okay APSSDC is completely for the peoples. Okay, thank you for the joining these sessions. Okay, close this session. Thank you.